Yeah, comes on everyone. Let's start off. Okay, so this was the last thing that we did. Let's go ahead. Others comes on. Let's say we have two observers. A का height is 2h. This is B. B का height is h. So distance between A and B is h. And at a distance h from B, there is a mirror. Find the minimum length of the mirror. If B can see himself. And the image of A completely. If you ever gone to a footwear shop, right? In the footwear shop, when you go and look at in the mirror, what you can see is only your legs, isn't it? And in your house, when you look at your mirror, mostly you can see only the upper half of your body. So there's a minimum length of the mirror I need so that I can see your complete self. Assume, there is no distance between the eyes and the head. Matlab, we are assuming B ka eyes are on top of the head. Neglect that height. It won't matter, but that will make your life little easy calculation-wise. There, let's get this. Nothing is given about the height of the mirror. You can keep it wherever you want, but it should be at a distance h. Find the minimum length of the mirror. So how do we approach this? Right, Viganchit. We have done this in foundation. Yeah, no. It's not the answer. First thing. So for the B to see himself, you want the light rays, right? Again, we're talking the top of the head, so light rays should go and come back. Actually, you can take even if you take with the eyes, there is no problem. And just make calculations easy, nothing much. So if you take the eyes here, so light rays from here will go like this. Light rays from the, they should reach like this. So light rays from the legs should reach the eyes. Light rays from the top of that should reach the eyes. That means the mirror should be this much. Making sense? So the light rays from the leg will hit the bottom part of the mirror. Light rays from the head will hit the top part of the mirror. If you see this thing here, this will be angles equal. So that is theta and that is theta. So if this is x, this is x. Similarly, this angle are equal. This is y, and then this is also y. Then you can clearly see this is x plus y. So 2x plus 2y will be h. X plus y will be h by 2. This is something which you learned in school. If you want to see yourself completely, you need a mirror of h by 2. Independent of the position, you can keep the mirror wherever you want and the thing still works. But there's one condition. The top part of the mirror should be at the eye level. So in order to see himself, that is the condition. You can keep the mirror wherever you want. For B to see himself, the length of the mirror is h by 2, starting from the eye level. The mirror must be placed from the eye level say below. That is the important thing. Great. Now, when you say I'm looking at A, what are you actually looking at? You're not looking at A, you're looking at the image of A, isn't it? So what you're looking here is actually image of A. So light rays from here are coming here. So it will feel like the light is coming from the head. And the light rays from the bottom are coming here. It feels like the light is coming from the legs. Isn't that how it will feel? So what you're actually looking at is the image of A. From here to here, this distance is 2h. This also will be 2h. That means for this person, this height will be 2h. This distance will be 3h. And you're keeping a mirror at a distance h from the person. You can clearly see it is a symmetrical triangle, similar triangle. So this height must be 2h by 3. Making sense? For height 2h, you got 3h. If the base is 2h, height is 3h. So if the height is h, the base should be 2h by 3. Similar triangles. And what about the eye level? The eye level starts from the center here. So this is the catch. So for you, in order to see A, we need a mirror of 2h by 3, where the eye level is the midpoint of the mirror. Midpoint of the mirror is at the eye level. Now we take the intersection of both. The common mistake is this. People will think 2h by 3, h by 2. So 2h by 3 is greater, so answer is 2h by 3. But what you're forgetting is, for this guy to see himself, I need a mirror of h by 2 starting from the eye level. For this person to see A, we need a mirror of h by 3 at the top and h by 3 at the bottom. You're getting it? So when I take h by 2 at the bottom, that is taken care of. But the problem will be the upper h by 3. So we take the intersection of these two. So you need a mirror of h by 3 above the eye level. You need a mirror of h by 2 below the eye level. So the answer will be 5h by 6. Is that clear, everyone? That's what makes this question a good one. Not only the length of the mirror, but the position of the mirror also matters. Because the question is minimum length of the mirror. Any doubts on this? All clear with this? Next one. Next one. Number of images for two inclined mirrors. First thing. So the images will form always at an angle theta. On the other side of the mirror. Meaning, if this is your mirror, we have done this. This was the last problem actually. If your object is here at an angle theta, the image will be on the other side of the mirror, making an angle theta. So basically the mirror must be an angle bisector. Clear with this? This is the we did last time. But when you have two mirrors, what will happen? The image of one mirror forms an image in the other mirror. So you'll get actually multiple images. So all images that form will lie on a circle. Whose center is the point of intersection of the mirrors. Meaning, if we take two mirrors like this, if the object is here, you can draw a circle. And you can see all images will lie on this circle, I1, I2, I3, I5, I6, something like this, where the radius of this circle will be this distance. So the object and the image will form a circle. Then you can clearly see here. So basically what you're doing is you took a circle and you made a slice of angle theta like a pizza. So if you divide 360 by theta, you'll get the number of slices. In that there is one object. So let's say a general formula for the images. So one image will be the object for the other mirror and so on. We will see the location also, how to find the location. So how do you find how many images are there? So if it is a main cell question, they'll just ask you the number of images. Case 1, if 360 by theta is even, then the number of images will be 360 by theta minus 1. Independent of position of the image. You can keep the image object wherever you want, you will get the same answer. Simple example, if we take two mirrors with an angle 90 degrees between them. So listen to this carefully. You'll understand why we are getting images like this. Let's call this thing M1. Let's call this thing M2. So first thing, if you keep an object here, so this is what happens. So these light rays are bouncing like this. So you'll get one image here, I1. Now what happens is this light rays from I1, they will go and hit this mirror M2. Now what will M2 think? M2 will think light rays are coming from O also, light rays are also coming from I1 also. Now M2 cannot differentiate between an object and image, isn't it? So these light rays will bounce off like this. So this will do what? This M2 will try to form an image here, and I3. You're getting it? So this I3, this is an image of I1 in M2. Similarly, the light rays which are hitting this, they will bounce on this. You're getting it? So that also will give an image that also forms at I3. So both the things will form at the same place. So this IO also will create one more image here, I2. So this is also image of I2 in M1. And this, all these four images will lie on a circle. They'll form a square actually. You're getting it? So I3 is an image ka image. Are you getting this? So I1 and I2 are first reflection ka images. I3 is a second reflection ka image. Then you can see there are total three images. So I3 actually there are two images, but the overlap, so you count it as one. Are you getting this? If 360 by theta is odd, then again we have two cases here. So n will be 360 by theta minus 1 if the object is on bisector. N is 360 by theta if the object is not on bisector. So this is valid if 360 by theta is integer. If it is not an integer, then you take the closest integer. Like example, if let's say 360 by theta turns out to be 6.93, then you take the smallest integer. What do we call this in max? There's a name for this thing, na? Smallest integer, greatest integer. क्या बोलते हैं उसको exactly? GIF. What is that? Greatest integer. What is the full abbreviation? Greatest integer function. So there. You take that and then you solve accordingly. Clear? Now let's try to find the location of these images exactly where they're formed. If I just want to find the number of images, this will do. All clear with this page? Any doubt so far? Now listen to this next one. It can be a little confusing. I'll show you one or two examples. Let's say we have two mirrors, M1, M2. Let's say we have an object here. This is alpha. This is beta. Object here. And let's say theta is alpha plus beta. Theta is the angle between mirrors. So the question is, I want to find the number of images and their positions actually. So remember the first point that we have, the image always forms an angle theta. So add theta to get an image. The next mirror. So listen once, I'll show an example that will things make more clear. So on the left hand side, we will write images formed in M1. So first thing, say, if this is 0 and this is M1, where will the first image form? The first image will form somewhere here at an angle alpha. Agreed? So we write alpha. So that is the first image which is forming on M1, right? Now look at this thing. So this image which forms here at I, this angle is alpha. Agreed? Now for M2, when you look at M2, so this angle is theta. So what will M2 think? M2 will think I1 is at an angle of alpha plus theta. So it will form an image here, this angle alpha plus theta. So how do we write this? So this alpha will create an image in M2 at an angle of alpha plus theta from M2. I'll show an example. We'll write it in more detail. Now that image which we formed here, now this image which is at alpha plus theta, again, this angle is how much theta? So this will form an image in M1, again at an angle of alpha plus 2 theta. So every time you just keep adding theta. So this will be alpha plus 2 theta. Similarly, this angle is beta. If you add angle theta, this will be beta plus theta. If you add theta here, this will be beta plus 2 theta. So beta ke image will form at beta plus theta image will form at beta plus 2 theta. So they'll just keep going crisscross. With numbers, you'll get a more clarity. So this is, let's say this is your alpha final and this is beta final. We need to do a little checking here. So we keep doing this till you reach 180 degrees. We keep doing this till reach 180. And if your alpha final plus beta final plus theta, if this comes out to be 360, meaning the last two images got coincided. So you don't count them. You count these two as only one image. Let me show you with numbers. Let's take a simple one first. M1, M2. Let's say this angle is 30 degrees. This angle is 60 degrees, and this is your object. Here, theta is 90 degrees, angle between them. Images in M1. Images in M2. Now, first thing, where will the image in M1 form? So this 0 will form an image here, 0 at angle 30. Agreed? .30 degrees. Let's call this thing I1. So if I draw this on a circle now, this is how it looks. See. This is I1. Are you getting it? So the meaning of this thing is the I1 image forms in M1 at an angle of 30 degrees from M1. That is how you read the whole thing as. Okay? So this 30 degrees, how much should you add? Theta, which is 90 degrees, will be 120 degrees. Meaning, see, now this I1 is the object and this mirror is the image. So 120 degrees from where? So the meaning of this thing is, so this is your I2. So this is the I2 is image of I1. In M2 at an angle of 120 degrees from M2. Meaning from this mirror, I have to rotate 120 degrees. So if I rotate 120 degrees, I will get I2. Making sense? Meaning, think na, if I extend the mirror, isn't this the reflection of this? Extend the mirror and drop a reflection. Got it? Now, if I add 90 to this again, this is exceeding 210. This is not acceptable. Done. You should not touch 180 or more than that. So you're done. Now on the other side, 60 degrees. So this is 60 degrees. If you add theta to this, what will I get? 120 degrees. So meaning, so this image, so first image is 60 degrees, right? So that will be somewhere here. So this is your, let's call it I3. That is 60 degrees from here. This is 120. 120 from where? This is 120 from this side. 90 plus 60, 150, sorry. So if you go 150 from here, this will be 150 degrees. This will be your I4. So this I2 and I4 both will overlap, isn't it? So when you go from that side or this side, the I2, I4 is overlapping. If you put 90 more again, it will cross 180, so you are done. What are the last two angles? Alpha final plus beta final plus theta. Here it is alpha final is 150 plus 120 plus 90. This is 360. Therefore, the I2 and I4 overlap. Is that making sense what we did? Got an idea roughly? I'll give you one more like this. You guys try, and then we'll see one or two examples. So this way you can actually find out where is the position of the image. We'll do one or two problems. You'll get used to it. Let's say this is M1. This is M2. Object. Let's say this is 10 degrees and this is 50 degrees. Get me the location of the images. If the question is number of images, that is easy. I can use the formula and finish it off. I want the location of the images. So put a circle and show me where these images are. Right, I'll give you 2 minutes. Let's see. 10, 110, 5 images. Yeah, that's it. So M1, M2, just let's put a circle. The first image in M1, right? So in M1, you'll get at an angle of 10 degrees. This will form an image at over theta is 60, 70 degrees. Then you will get a 60 plus 70, 130. If I add 60, you will go to 190. So I won't do that. So this guy, so if I call this thing I1, if I call this I2, and if I call this I3, so I1 is at a 10 degrees from M1. That is the meaning of this. If you're on the M1 side, that means you're at 10 degrees from M1. This is I1, this is 10 degrees. Then I2 is 70 degrees from M2. So from this line, you have to draw 70 degree. Remember, this is already 60. So 70 will be somewhere here. This is 70 degree. I3 is 130 degree from M1 again. So from here, you have to put 130. This is 90. Again, I'm just roughly drawing them. This is 130. Clear with this? Then for this guy, this will be 50 degree. Add theta, that is 60. This will be 110. Add 60, you'll get 170. And you can clearly see here, the final angle is 130 plus 170 plus 60 is coming out to be 360, meaning the last two images are coinciding. This is I4, I5, and I6. When you actually put it on a graph, you will see that also. So I3 and I6 coincide. So I4 is 50 degrees from M2. So somewhere here, this is I4. I5 is 110 from M1. So that will be somewhere here. And then I6 is 170 here. So this will be I6 and this is 170. Clear with this? You can see the angles also 170, 130, and 60. That is coming 360. Got it? So the last two angles and theta will add up. So the overlap. So we got 5 images here. And this will be the positions. Let's see one more. Let's say this is 20 degree. This is 30 degree. Put them on a circle. Don't count 180. 180 you will never get, because think about it. Logically, 180 doesn't make sense only. The light rays, right, will not go like this anytime. The meaning of 180 light rays have become parallel to the mirror, so we'll not take that case. This is fine. So there is no image only here. So there is, so if you try to add also 170, 120, that's your final there. Plus 50, that is 340. So you're safe actually. 170 plus 120 plus 50 is 340. Yeah, this is not equal to 360. So images don't coincide. I6, I7 don't coincide. You get 7. You don't count that 180 there. So I1 is at 30. This is I1. This is 30. I2 is 80. 80 from M2. That is the meaning of this. I2 is at an 80 degrees from M2. I3 is 130 from here. And this is I4. This is 20. This is 70. That's 170. Yeah, there's a 120 also. And 20 meaning almost it will be somewhere here. And 170 will be somewhere here. Clear with this? So there'll be 4 images in M2, 3 images in M2, and 4 images in M1. Got this, everyone? Clear? Next one. That's about the images that you form when you have, two mirrors touching each other, inclined mirrors. But what if the mirrors are broken? What happens if you have an incomplete mirror or a partial lens? Let's say we got a mirror here and you're standing in front of it. Right? And we have your image. Now tell me, if I take a hammer and break half of the mirror, what will happen to your image? Will I get only half of your image? So the thing is, if you look at the light rays, understand, we always take 2 light rays, but there are infinite light rays which are hitting the mirror. Now, if you break the mirror, let's say if you only a part of the mirror, the light rays are still hitting the mirror. There are multiple light rays which hit this part of the mirror. And if you retrace them back, the image is still there. The image will still form at the same place. But the problem, in order to see this image, you have to be in the field of view. Remember that auto example which I give you normally? If you sit in an auto in the middle seat, you can see the driver. But if you shift to the side, you can't see the driver. The image is still there at the same place. You are not in the field of view. You will see a complete image without any distortions. Meaning, if the person is standing here, he can see the image. But if you take an observer and keep it here, the light rays are just going off straight here. He can't see. So there. So if you break a mirror or if you take a part of a lens, the image will still be at the same place, right? Without same size, no distortion, nothing. The only thing that will change is brightness. Because when you have a full mirror, you're getting a lot of light rays which are reflecting. When you have a part of a mirror, less light rays are reflecting. So part of a mirror or a lens forms an image at the same place as a full mirror. Or lens with decreased intensity or decreased brightness. That is a catch. The brightness will be less. Did you ever notice this thing? When you go to a shopping mall and buy a dress, normally girls can observe this more clearly. They have better eyesight than boys. That's true, actually. You must have heard in school, rods and cones. Girls have 50% more rods and cones in their eyes compared to the boys. We are literally colorblind. If you don't trust me, you should go to your sister or mom now. You should open their lipstick box. Open that, and you ask them to tell the colors. Let's say there are 7 lipsticks, okay? And if you ask me to show red, I will say, okay, red, dark red, light red, 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 and little orange. That is how you and I will see. You ask the same thing to your sister or someone, right? They will say, this is red, maroon, baby pink. They will have a color for each and everything. So in the beginning, I used to think maybe I'm colorblind or maybe I'm insensitive. But later on, when I noticed, right, this is with all the boys. And then I said, like, how can this be? Then when I went and started searching a bit, I found out boys ka eyes, right, we have less rods and less cones, 50% less sensitive. So we can't perceive the colors the way girls can perceive. Right? They have I never heard those names also. Matlab, red, pink, baby pink, maroon. I said, what the hell is baby pink? I have no idea, but theek hai. So that is there. So this is one thing you notice, when you go to a shopping mall and you buy a dress, you try it in the trial room. It feels good. You buy the dress, you come home, wear the same dress and look yourself in the mirror and you feel like, okay, this is the same dress, but it doesn't feel the same way it felt in the mall. Kabhi hua? And for boys, for us, it feels like this. Let's say you want to go for a haircut. You look at yourself in the mirror. You feel like a jungly, right? Arey, I'm looking like a jungly guy with a lot of hair and all. But you go to the saloon and let's say you're sitting there waiting for your turn. You look at yourself in the mirror and you feel like, not exactly. I'm looking good only. Kabhi laga? The thing is, again, go back to this thing. In the shopping mall, when you're trying your dress in the trial room, how many mirrors are there? The mirror in front, left, right, back, everywhere there is a mirror. That mirrors are not there just to, get a view of your dress. There are so many lights. There is so much reflection happening. Your image get a very good contrast. Most of the dresses will look good on you. The same way, when you go to a salon and look at yourself in a big mirror, your image looks very clear, right? There is a very good contrast and you look really good. But at home, you have a small mirror. So when you look at yourself in that small mirror, the image is really not that as bright as what you see in that saloon or the shopping mall. And on top of it, shopping malls, you must have seen the lights they use, right? They look a little weird only. Sometimes you don't understand what color you're buying also. So yeah, a few things you can do like that. So there was a question when I was in 11th or 12th. There was a question someone asked. Some guy came. The question was this: tell me what do you guys think is the answer. So let's say you are a photographer, right? You went to Kenya to take a photograph of a zebra. Unfortunately, there are no zebras there, right? So you came up with a brilliant idea. You said, okay, but you found a white donkey. So you have a white donkey there. ठीक है. Completely white donkey. So the idea you have is this. You said, okay, I will take a lens. And let's assume the donkey remains at perfectly still without moving and all. So you will take the lens, you will take a black color marker, and while looking at the lens, you paint the lens with a black marker. So when you look at this through the lens, it looks like exactly a zebra. Do you get in the logic? You took your lens and you painted the lens with a black marker, the front part of it, and when you look at through that, it looks like a donkey. Now, if I take a photograph, will I get a donkey? Will I get a zebra? Will I get a donkey? Is the question clear? You got a white donkey, you want a photograph of a zebra. You took a lens, this photograph lens, and you marked with a marker, black lines, and then when you see through the lens, it looks like a zebra. If we take a photograph, do we get a donkey? What is the catch? Now, chalo, think of that thing. Now, I have glasses. I'm looking at you. So if you take a marker and put a black line like this, so do you get a black line on your face when I look at you? So how do I exactly see? This is what I was saying. So if I close half of my lens, I can still see your full image, right? I can't see half of you. The reason the light rays from you are still entering this part of the lens, isn't it? So the points which you blacked, chalo, that is gone. So this is like a partial lens, isn't it? When you coated them with black paint, it is like you're having a part of a lens. And just now I said a part of a lens still will pass through the image. So this part of the lens which is not marked, so all rays from the donkey will pass through this part of the lens. Pass through the unshaded part. So what will be different then? Your image will be dull. You will still get a white donkey. So we get a picture of a white donkey with decreased brightness. You won't get a zebra. Because to take a picture, you need light rays from every part of the donkey. And you are getting it. You even if you cover half of the lens with black paint, the other half of the lens is still getting light rays. So then how to get a zebra? Go and paint the donkey with black paint. Don't get the you don't get light rays from the donkey from that spot. You need to paint the donkey, not the lens. Okay, that's how you can become a wildlife photographer. You get a picture of white donkey with decreased brightness. There, so that is the main story there. Even if you have a part of a lens, you still get a full image. No, you adjusted the lens in such a way the lines are looking like that, right? See, you are looking like that. The camera ka lens will get all the light rays.
So why don't we get all the light rays?
Where?
So like camera gets all the light rays, so light rays will pass through the parts which are unmarked. That's why we see a
Yeah.
white donkey that's dull. So technically that should also apply for our eyes, right?
Technically, you also should see a white donkey. This guy should not be able to see only. But yeah, let's say somehow you saw through the lens. You painted so much, you started visualizing.
Okay, sir.
Technically, what you said is right. Or maybe lens ka aperture is big and eye ka is small, so maybe. Technically, you should still see the white donkey only. That is one. Another way of asking this question is, right? What happens if I have a mirror like this? "90 degrees and 90 degrees and object." Now, how many images will form? You broke the mirror. There is no mirror here. Think of like this, na, Vihan. If you put a pen in front of you and if you just close one eye, when you see through the lens, you see through only one eye, na? And if you put something in front of me, see, I can block you with just this thing. I can't see you like this.
Yes, sir.
So maybe when you're taking this camera ka lens, right, it's like you get more light rays from every other direction. You can just put a finger in front of me and you can block my screen if you just close one eye.
Yes, sir.
So basically, the field of view must have become decreased less, because you're keeping it too close. But maybe a camera is longer, so you can get more light rays.
Yes.
Something like that. You can adjust a bit. That, yeah, technically what you're saying, it is true. What about this guy? How many answers will come for this one? Nah, it won't be the same. See, the reason here. So from point O, when the light rays bounce off here, when you extend them, you get an image I1 here. But see, there is not a single light ray which will hit M1 and will go here, isn't it? There is not a single light ray which will go from M1 to M2. That means M2 will never know that I1 exists. Previously, remember what was happening? The light rays used to hit M1, then used to bounce here and go here. Then M2 used to think I1 is also an object. But now you're not getting a single light ray going from here to there, so you will never see this thing. So these light rays are just going off. Similarly, here also, every light ray that bounces here is going off. There is not a single light ray from M2 to M1. I3 will never form. Light rays from M1 never reach M2 and vice versa. Remember, I3 was an image formed due to I1 on M2 and I2 on M1. Now that will never happen. So I3 will never form. There will be only two images. So if you want three images, all you need to do, right, just extend the mirror little. Even if you extend the mirror little, suddenly you'll get a third image. These letters will bounce here and I3 will form. Clear with that? So that I3 was forming because of double reflection. So light rays from M2 need to reach M1. This is another way of asking. So be careful. Just because if I put two mirrors, 90 and all, you need to understand the light ray should reach in order to form an image. Any doubts on this? Yeah, that's a bit about plane mirrors. The next thing, spherical mirrors. So before jumping into the spherical mirrors, we will see a parabolic mirror. So if you take a parabolic mirror, so if you send parallel light beam, they will meet at the focus. This is actually the property of a parabola. So parallel rays after reflection meet at the focus. Did you ever see this Enfield headlight? It kind of looks like this only. It's a paraboloid. So there, if you keep the bulb at the focus, the light rays go parallelly. So this is how you create a parallel beam. The light rays can go really far. These are normally used in telescopes. We will see later on, we have something called a reflecting telescope. Because when you're taking light from the space, right, they create huge parabolic mirrors. You can collect a lot of light to analyze, because the light which is coming from that far is already weak. So you need a lot of light. Unlike your photographs now, you take your camera and take a photograph at people. Telescopes don't work like that. You know what they do? If you're looking at a certain spot, the camera is pointed towards that spot for days. 15, 20, 30 days, they keep that camera focused at one spot. So literally you're taking millions of images. They take a lot of images, and then they use software, they keep on overlapping one image on another. And the data, they just keep on making it better and better. The same technology we use in phone nowadays, isn't it? Burst mode. You take a phone, when you click it, it takes some 15, 16 photographs and it takes the best of it. Or it does a remix of all those photographs and gives you a good picture. So every technology that you're seeing, right, these are actually designed for either military or some space purposes. And later on, people have taken them and started using for civilian purposes. Now, so we use all the technology to make what? The stupid Snapchat filters, Instagram filters. You take photographs to dog ka face aayega. So unfortunately, you take the world's best mind, make them sit and make them do all this shit. Yeah, obviously, they get paid more for doing that. So who will not do it? Now, the problem with the parabolic mirrors, they're kind of little difficult to make and they're expensive. So we want to use spherical mirrors, economics, because it is cheaper to make. But spherical mirrors have a problem. If you take a spherical mirror, it's always like this. It's always economics versus accuracy. Until unless you don't worry about the money, then accuracy you can make it. As you want more and more accuracy, you have to spend more and more. The problem with this, if you send parallel light rays, they don't meet at the same spot. The image will be distorted. This is called spherical aberration. Aberration meaning error. Spherical meaning it is an error because it is a spherical surface. The images will kind of look like this. There. This people with glasses will understand. If you remove your glasses and look at lights, this is how they look, isn't it? They don't look like single spots. The bulb will look like completely blur. So what we have been doing so far, right? We are actually using an approximation. So how do we use them? We use an approximation. So let's see that. So how do you make a mirror? You take a sphere, cut it. This is called principal axis. This is your center. This is your pole. This is your radius. This part is called aperture. So aperture is the region where the light rays enter. So depending on how much you cut, you can change the aperture. You want a big aperture so that more light rays can go, the image can be more bright. This small r is the radius of aperture. So be careful, radius of curvature, radius of aperture are two different things. The radius of curvature doesn't change on how big is the piece. You can have a small piece, big piece, radius of curvature is same. Aperture will change on the other hand. So if you take this and if you silver it on the outside, and if you silver it inside, this is a concave mirror. This is a convex mirror. Clear with this? Take a small break, come back by 9:40. Any doubt so far?
Question.
No.
The one we did for the number of images one. So in that, why can't we consider 180?
Yeah, 180 meaning what? The image will be where exactly? I3 M2 का 180. So you're saying, see 180 का problem ये है, I told you. 180 means you're saying the light rays have hit here and become like this. वो कभी नहीं होगा. You can always take a case, the light rays are getting closer and closer ना.
Yes.
180 कब आएगा? At infinity, when the light rays become like this, that will never happen.
हाँ sir, समझ में आ गया. Thank you, sir.
चलो, come back in 5 minutes. Yeah, let's start off. So what we do, since we still want to use spherical mirrors, we take an approximation. So if you take light rays very close to the principal axis, we can assume they're meeting at a single point. That is, if this h is much less than r. These are light rays very close to principal axis. These are called paraxial rays. So their entire ray optics is based on this. We'll be studying lenses, everything for paraxial rays only. If the rays are not paraxial, we don't know what to do. So we'll not study them. Example, when it's much smaller, we are talking something like, let's say h is 2 mm. Radius is 10 centimeters. We can assume these rays meet at the point. And this is what we call as focus. And this we have done in a problem, if you remember, I think third problem or something. I think we got Cx is equal to r minus r by 2 sec theta. If theta tends to 0, that is h is tending to 0. Then your Cx will tend to r by 2. So there, that's your focal length. Clear with this? So you can't use this focal length thing for anything. It has to be used only for paraxial rays, and that's what we'll study for the entire ray optics. Clear with this? So yeah, we are okay with this kind of a small error because it's more cost effective. Meaning, so the lenses which are using people with glasses. So if you actually measure the radius of this glass, that could be something like 7, 8, 10 centimeters. But if you see the light rays that are entering here, there's only like what? 1 centimeter. So this thing, when you actually remove it and see, that would be actually part of a big sphere. So the glass which you are wearing, the aperture is small, but the radius of curvature is big. So we got a big radius of curvature. We are taking a small piece here. So the light rays which are entering through your glass here, these are paraxial rays. If you ever been to this glasses shop now, I don't know whether they do that right now or not. Long back when I went, right, they used to show like, when you tell them, no, your power is so and so, that guy used to bring 2 glass pieces. And used to show like, sir, you want to use this glass or this glass? Like, I said, what is the difference? This thing is a low refractive index glass. It will be thicker. This is a high refractive index glass. If you use this, your glasses will be thinner. Ever heard something like that? I don't think nowadays they're giving that option. Or sometimes, yeah, must have heard it. So they used to show that. The thing is, the low refractive index glass, now the glasses will be thicker, but it is cheaper. The high refractive index glasses will be thinner but expensive. So that was a choice. But I don't know nowadays anyone is giving that option or not. But yeah. This is the most important thing in the whole chapter, sign convention. Like I said, if you know your sign convention and if you know the formula, you can handle most of the problems. Mains level, you'll never have a problem. Advanced में फिर भी थोड़ा सोचना पड़ेगा, but फिर भी compared to mechanics, it will be still easy. So sign convention, listen to this carefully. There are 2 types of sign convention. One is your Cartesian coordinate. Second thing is the direction of the light ray. We will use the direction of the light ray. So in case you're using something else, that is also fine if you're comfortable, but if you're using the same thing, then it is great. So the first thing, the direction of the incident light rays is taken as positive. The reason for this, it's like one thing that I noticed when the light ray is going between mirror, lens, mirror, multiple things, it is always better to follow the light ray. You'll see, I'll show you an example. Second thing, all distances are measured from the pole. So you always take the pole of the mirror as an origin. Or optical center of the lens. So for a lens, it is called optical center. All distances above principal axis are positive. And below are negative. So this is the terms that we use. U is your object distance. B is your image distance. R is your radius of curvature. F is your focal length. Let's do with an example. Say. Same example, I used it before. We have a lens, we have a mirror. Object is there. Let's say light rays hit the lens. They will go combine here. Let's just be I1 hits the mirror, bounces off. This is your I2. So I2 will act like an object. Light rays will come from here. They will pass through the lens. They will again merge somewhere here. This is I3. Do you remember this example? No. Listen to the convention carefully. Listen to this thing. First thing, if you ask the lens, right? How are the light rays coming? So for the lens will say, okay, object is here and the light rays are going this way. This is your direction of light rays. So we take the right side as positive. Direction of incident rays. Meaning the pole is the origin, 0, 0. This is your positive x-axis. This is your negative x-axis. Where is the object? Object is here. Where is the image? Image is here. So what is the object distance? So U will be, object is which way? On the negative x-axis minus OP. What is the image distance? Plus PI1. Is this making sense, everyone? Wait, it is a lens, na? Let me take it as L. So this will be minus OL and this is plus LI1. Is that making sense? Any doubts on this? Please ask me. Light rays are going to the right. So right is positive. So right side is positive x-axis, left side is negative x-axis, and the center of the lens is the origin. Object is on the negative x-axis, so coordinate will be minus OL. Object image is on the right hand side, so plus LI1. Now, if you ask the mirror will say, okay, my object is I1. Again, light rays are going this way, so this is positive. So this is positive x-axis. This is your negative x-axis. This is important, right? Because one sign you mess up and the whole question goes for a toss. And the image is somewhere here. All distance are measured from the mirror. So this will say U is equal to minus MI1 and V is equal to plus MI2. Is that clear? All okay with this? So now when you talk about the mirror, the distances are measured from the center of the mirror. You're getting it? So for each system, the origin keeps changing. Now when the light rays come back again, here things will change. So if you ask this lens, boss, where is your object? The lens will say my object is I2. That means light rays are going this way. Meaning this is positive. This is negative. Are you getting it? You always follow the direction of light rays. You keep going with the light rays. And your object is here I2. Your image is here I3. So this guy will say, again, this is a lens L. So you will be, the object is on the negative x-axis. So minus Li2. V is equal to plus Li3. Is this clear, everyone? The plus and the minus signs. One advantage of this thing, right? You are always, can you see you're doing only one at a time? When I talk about the lens, I don't talk about the mirror. So this thing is actually three simple problems. One lens, one mirror, one lens. Is the convention clear, everyone? This is for U and V. Now radius of curvature also has a convention. Can I go ahead? Any doubts on this page? We'll do some problems. So sign convention will come in, that will take care of it. So if you talk about radius of curvature, let's say we have a concave mirror. And let's say radius is 20 centimeters. Again, same story. So let's say object is here. So light rays are going this way. This side is positive, meaning this is your positive x-axis. This is your negative x-axis. So how do you find the radius of curvature thing? So for this radius of curvature, if you make this into a full circle, where is the center? Center will be here. So where is the center? On the negative x-axis. So therefore, here the radius R will be minus 20 centimeters. Suppose if you take like this, R is 10 centimeters. Object is here, light rays are going to the right side, so this is positive. This is your positive x-axis. So this is how you find the radius of curvature. Always complete the circle. If you complete the circle, the center is here. So here the radius of curvature is plus 10. So step 1, direction of light rays. That is positive x-axis. Step 2, where is the center? Is it on the positive x-axis or negative x-axis? Where is the object? Positive x-axis, negative x-axis. Where is the image? Positive x-axis, negative x-axis. It is on the positive, it is plus. Negative, it is minus. Distance are measured from the pole. Now, the interesting thing is a lens actually. Suppose if I take a lens like this, let's say R2 is 10 centimeters and R1 is 20 centimeters. And let's say object is here. Now, how will you take this? In a lens, there are two radius of curvatures. So light rays are going this way. So this is positive, right side. So this is my positive x-axis. This is my negative x-axis. So listen carefully how we do this thing. So for R1, complete a circle. The center will be this side. For R2, complete a circle. The center will be this side. There. So your R1 is on the positive side. So R1 is plus 20. R2 is on the negative side. R2 is minus 10. Are you getting the convention, everyone? So there are two spheres there. So complete the circle, see where are the centers. Let's say object is here. Can you tell me what is R1, R2 now? So depending on where you keep the object, R1, R2 will get messed up. Let's see. So what is this thing? So same story. So light rays are going this way. So this is your positive x-axis. So R2 ka center will be here. R1 ka center will be here. So R1 is on the positive side, +5. R2 is on the negative side, -10. All got the convention? There. If you understood this much, your sign convention is done. Matlab, for the entire ray optics, is the sign convention we'll use. Any doubts on this? Next thing. For the spherical mirror. Now the formulas, derivations will not be doing it. They're not important because even the derivation itself has a lot of approximations. So they really can't mess up anything there. And HSCM also it is not there. So derivations are a waste of time for now. So if you have a spherical mirror, the formula is given by, this is your pole. One by V plus 1 by U is 1 by F. You can note it down. Focal length F is given by R by 2. Magnification M is nothing but height of the image by height of the object, which is given by -V by U. There, you should know these three formulas. So few precautions here. U, V, and R should be taken with sign convention, not the magnitudes. U is the object distance, V is the image distance. Second thing, these are valid only for paraxial rays. Third, this is valid only if the object is on the principal axis. If the object is not on the principal axis, there is a way to do, but you can't use this formula directly. There, as long as you know these three formulas and the sign convention, we can see the problems. Yeah, there will be here and there little variations, but that is a basic thing. All clear with this? Let's see some questions. Everyone copied the three formulas. Concave mirror radius is 20 centimeter. This is object. This is 30 centimeters. Find the position of the image. Convex mirror, radius 20 centimeter. Object is also 20 centimeter. Just formula substitution. Find the position of the image. Get this straightforward formula substitutions. For the first one, lighters are going this way, so right is positive. So object is on the left-hand side, the U is minus 30. Radius, center is also on the left-hand side, minus 20. Therefore, F is minus 10 centimeters. Applying the formula, 1 by V plus 1 by U is 1 by minus 10. So we get V is equal to minus 15 centimeter. So how will the image look like? So if you try to trace this, so the minus indicates the image is on the left side of this thing. This is your negative axis, and 15 centimeters from the pole. Are you getting the meaning of that minus 15? Same thing here. Lighters are going this way, so this is your positive x-axis. Center is also on the right-hand side. The U is minus 20, radius is plus 20, and the focal length is plus 10 r by 2. Applying the formula 1 by V plus 1 by U, 1 by F. Solve this, V is 20 by 3 centimeters. If you actually try to trace the diagram, this is important. You should know how to draw the picture every time. The lighters are bouncing off like this. This is the image. This is a virtual image, it's not real. Clear? There, just the sign convention and the formulas. So, any doubts on this? All clear? Going ahead, next one. Next one. We have a convex mirror. We have a rod here of length L. This is also 20 centimeters. It's a thin rod. Case 1, L is 20 centimeters. Case 2, L is 2 millimeters. Find the length of the rod image. In the first case, the length of the rod is comparable to the radius. In the second case, the rod is very, very small. And the distance from point B to the pole of the mirror is 20 centimeters. Get the So this thin rod, the rod is on the principal axis. It has no height, it is only the thin rod. There, give it a try. Just give it a try. I'll back in a minute. So how do we do this? 4/3, 4/3, 5/3. Okay. So what is the idea in these kind of problems? If I can find the image of A and find the image of B, let's say A ka image is somewhere here, B ka image is somewhere here. So can I say all the points between A and B will lie between these 2 points? So then the difference in the 2 images should be the length of the image. Is that making sense? That is how we solve this. If you find images of A and B, then all the other points must be between them. Well, that's fine. So lighters are going to the right, so right is positive. So first I'll find for A. U is minus at least 20 centimeters. So U is minus 40 centimeters. R is plus 20, F is 10 centimeters. Substitute in the formula 1 by B plus 1 by U is 1 by this. That would be 6 by 40. 20 by 3 centimeters. If I do the same thing for B, U is minus 20. Please ask me anywhere you got confused with the sign or something. Focal length is still the same, 10 centimeters. So 1 by V plus 1 by minus 20 is 1 by 10. This will be 2. Did I goof up something? Yeah. 5 by 40. 5 by 40,000. That is 4. 5 by 40 though. That is 8 centimeters. This is 20 by 3 centimeters. Yeah, I'm getting 0. Anyway, so the A ka image is somewhere here. Let's call it A dash, and B dash is somewhere here. So we got this length will be 20 by 3, and this length will be 8 centimeters. So A dash, B dash will be 8 minus 20 by 3, which is 4 by 3 centimeters. Got this? Now, what about when the length of the object is very, very small? We can do the same thing. We can do the same stuff, and then we can use binomial approximation, but there's a much better way. 1 by V plus 1 by U is 1 by F. Differentiate on both sides. Since you said it is, you can see that L is very, very small. L is 2 mm, which is much, much smaller than R. So this will be minus dV by V square, minus du by U square, minus dF by F square. This guy is constant, so 0. So we get dV is equal to minus du v square by u square. Now try to understand the meaning of this. When you took this image, what is u? U is the object distance. Since the rod is very small, if I say b ka distance is u, can I say a ka distance is u plus du? So du becomes the length of the object. Similarly, dv becomes the length of the image. Are you getting the logic there? Let the distance of a be u, let the distance of b be du plus du. So du becomes the length of the object. Again, it should be small. This becomes the length of the image. Be careful, you can use this only when the images are small. Object is very small. If it is big or comparable, do the previous method. So there, I can just treat it as a point object. So we get v is 20 by 3. So if you substitute the formula here, we get dv, du will be 2 millimeters. This will be 20 by 3 whole square by 20 square. You get minus 2 by 9 mm. Minus indicates the direction this thing got reversed. Got this? This is how you do for small objects. Any doubts on this? The another way to do brute force is, yeah, that will be complex actually. You will do for 1 by v plus 1 by 20. The other will be 1 by v plus 1 by minus 20 plus 2 mm. So when you do this, you take a binomial approximation there. It will be quite lengthy, and end of the day, you'll get the same answer. See, the moment you say I will use binomial approximation, you are saying it is so small, even differentiation is makes sense. Getting it? So it works out. All clear with this? There, that is the two cases of the same problem, length of the object. So length of the image. Let's see one more. Let's say we have a convex mirror, radius r. We got a plane mirror. We got an object here. Let this distance be x. Let this distance be y. So x is the distance between the plane mirror and the object, and y is the distance between the plane mirror and the convex mirror. So find the condition if you can see only one image. Normally, if there are two mirrors, shouldn't you see two images? For some reason, you can see only one image. What's happening and what is the condition? So what are the catch here? The reason you're seeing only one image is because the plane mirror ka image and the convex mirror ka image both must be overlapping. That's the theme there. So since both the images overlap, you can't differentiate between them. You think there's only one image. The image due to the plane mirror and convex mirror overlap. So the plane mirror image will form where? If this is X, the plane mirror image also will be X. So that must be somewhere here. If that is X, then this distance is X minus Y. So what is U? Remember, light is going to the right, right is positive. So U is minus of X plus Y. What is V? Plus of X minus Y. Focal length is plus R by 2. Got the thing with the signs? Then substitute in the formula 1 by V. 1 by minus X plus Y. 2 by R. This will be X plus Y minus X plus Y by X square minus Y square is 2 by R. X will cancel, we will get R into Y is equal to X square minus Y square. There. As long as you satisfy this condition, we will get only one image. So plane mirror, it is straightforward. If you're at a distance X, image will be at a distance X. But for the mirror, the distance is measured from the pole. So for the convex mirror, the image is at a distance of X minus Y. All got this? Any doubts on this? That is one thing there. Next thing, tracing of images. This is one important thing, especially for theoretical questions. If you have done in school also, you must have done this. Did you do something like this in school? If the object is at infinity, image is at focus, object is at center, image is that. I'll show you anyways, but. So normally whenever you want to trace images for any system, right, there are some few special light rays. In case of spherical mirrors, we have 4 special light rays. So you choose any 2. After reflection, see where they meet. Wherever they meet is your image. The first thing is the standard one. If you send a parallel light ray, it passes through the focus. If you send a light ray through the focus, it becomes parallel. If you send a light ray through the center, it will retrace the path. If you send a light ray through the pole, it will bounce in such a way the angle of incidence is equal to angle of reflection. There, these are the 4 light rays that you have for mirrors. So whenever you want to find an image, you actually take any 2 of them. For example, see, this is how they normally trace it. Let's say this is the center and this is the object here. You want to find the image of this guy. So I will send a light ray like this. It will go through the focus. Then I will send a light ray through the center. It will come back through the center, meaning this is the point of intersection. Na? So that is your image. You're getting how we trace it? For example, if you have somewhere here, so if I send a light ray through this, it will become parallel. If I send a light ray through the pole, it will cross here. So this is the image. So choose any 2 light rays, send them, and wherever they meet is your image. So we have cases here. There. The first case, the object is placed at infinity. The image will form at the focus. It is real, it is inverted and highly diminished. You almost get a point. If the object is placed between infinity and center, the image will form between center and focus. It is real, inverted and diminished. Have a look at this. So here, this height of the image will be less than height of the object. These things you should know. So when you're solving problems, right, intuitively you'll get an idea. Okay, if you get a wrong answer, you'll know this is wrong. Did you guys do something like this in school? But have a look at this. Any doubts on this page? Clear, na, Devansh? Ahana, Niharika? Clear this. Next thing. There's a total 6 cases for a concave one. If you place it at the center, the image will be at the center and inverted. If you place it between focus and center, image will get magnified and it will be beyond center. If you place it at focus, you'll get parallel light rays. If you place it between focus and pole, you'll get a virtual image. Have a look at the cases. For concave, there are the 6 cases you have. All clear with this? For convex, we have only like 2 cases. Because in convex, no matter what you do, you'll always get virtual image. If you're at infinity, image will be at focus. If you're at any other place, the image will be between focus and pole. It is always virtual, erect, and yeah, it is diminished. Do you know how they'll ask theoretical questions? An object is placed in front of a mirror. The object is magnified and erect. Which mirror is that? The object is magnified and erect. Which case is that? Concave mirror in which case? So where is the object placed? I can ask you more. Where is the object placed? Between center and focus, focus and pole, ऐसा options होगा. 6th case, isn't it? This is the only case if you see where the image is erect. If you see in concave, na, all images are inverted. Right? If it in convex, all images are erect, but the problem, none of the images are magnified. The only case is the case 6 in concave. The image is erect and magnified. They'll ask you one more question like this. In a concave mirror, the height of the object is 3 times the height of the image is 3 times the height of the object. The height of the image is 3 times height of the object. Find the position of the object. How many answers are there? There are 2 answers. The problem with that statement, I didn't tell you whether the image is inverted. It could be this case also, na? It could be inverted 3 times or it can be erect 3 times. There are 2 possible answers for that. Are you getting this? So let me ask you one more theoretical question on this. So this would be a good question actually. I think if you got this, you understood this. Let's say if you take a concave mirror, let's say we have an object here coming from infinity in a straight line. Draw the path of the image. If this object is going in a line, how will the image go? This is the kind of questions you'll get. There'll be 4 options, 4 different paths. The object is going minus infinity to pole. It is above the principal axis. Take a minute, then I'll show you. I'll give an idea. See, instead of jumping directly onto this, think of like this. Imagine we have one pole here at infinity, one pole somewhere here, one pole here, one pole here, one pole here, one like this. So let's say there are 7 arrows like this. Can you draw these 7 arrows images? If you can draw the image of the 7 arrows, and if I join all their heads, isn't that the path of the image? Is that making sense? So where is that arrow 1 ka image will be? At focus. And it will be a point, isn't it? So 1 will be here. Where is 2 ka image will be? Between center and focus, and it is diminished. So it will be something like this. Where will 3 be? 3 will be exactly on the center, same height. 4 will be somewhere here, magnified. 5 will be infinity, meaning this guy is going like this. You get in the path? But once you cross this, where will 6K image be? So this 5K image, there is also one 5K image here at infinity. 6K image will be somewhere here. 7K image will be somewhere here. That is a virtual image. If you cross the focus and start going towards the pole, the image will start going on the right-hand side. It's virtual, isn't it? And when you're at the focus, you can say, since the light rays have become parallel, I can also say they're meeting on the right-hand side. You're getting it? If you are on the focus slightly left-hand side, image at minus infinity. If you're slightly on the right-hand side, you're on the plus infinity. Because when the light rays have become parallel, it doesn't matter. You can say they're meeting front or they're coming from back. Is this path clear, everyone? Any doubts on this? So this is the kind of questions you'll get, and should know how it looks for each part. Can you do the same thing for this guy? Convex के लिए. This is kind of easy. Luckily, you won't have so many arrows here. One arrow at infinity. One arrow here. One arrow here. Bas 3 arrows tha. So the infinity wala arrow will be at focus. Second will be diminished. Third will be the same height at the pole. It will be like this. Making sense? How is the path? The image starts at the focus and it goes like this. It starts becoming flattish. As you get closer to the pole, the image starts getting the same height as an object. Clear, everyone? Yeah, this is how they make this is an easy one. This is a good one. Most people will forget the virtual one. I can ask a lot of questions. As the object approaches the focus, what happens to the acceleration? Is it going faster, slower? You can ask a lot of things like that. Clear? So I'll just put a table here. There's just a thing. At minus infinity focus and all, but yeah, the pictures are better. Okay, with that, we'll wrap up for that. And next class, when we catch up, we'll continue with more. Like spherical mirrors, we'll do more problems. We'll see the graphs and all that stuff. Next class, mostly you should be able to wrap up the mirrors. If mirrors are done, then maybe we'll do a little introduction of refraction also. So, but like I said, we are done with current recently. So please focus on the current. At least till next Monday, try to finish your current ka jo bhi backlog hai. Whatever material, whatever book you're solving, finish it off. And this week ka test is electro, Gauss law, capacitor, current. Literally, like I said, entire electromagnetism ka, these are the starting topics which we did. So that should give you a good practice. Okay, with that, we'll wrap up for the day. We'll see you again on Friday as usual at the same time. So any doubts in the class notes, anything, stay back and ask, or else you're free to leave. So take care.